Hey math fans, Alex here, and in the last video we introduced some basic aspects of combinatorics, including just how to count situations with a certain number of objects in one group and a certain number of objects in another group, and we asked like how many pairs of objects exist. Okay, so I want to go back to this example and show you kind of a shortcut to theorem 1.2. It's not really a shortcut in the conventional way, but it's like a little illustration that I'll use from time to time. So usually what I'll do is I will, in the case of 3 dice, I will draw 3 blanks. And each blank represents a different group with different numbers of outcomes. And this, of course, represents the total number of outcomes. And this is maybe the first die, second die, and the third die. We just have to ask how many different outcomes in each of these. Well, there's 6 for the first die, 6 for the second, 6 for the third, and then we just multiply those up to, again, get 216. So I'll be using that occasionally in this video, so I just wanted to introduce that now. Here's our second example. And the second and the third example are probably the most important in this lecture because they're going to talk about how to count when you're sampling with replacement. That means you have some sort of group of objects. You take one, then you place it back, and your population does not change after every single sampling. Okay, so let's start off with sampling with replacement. So the idea behind with replacement is as follows. Suppose we have a total population of n distinct objects. Okay, and we can label those however, A1, A2, all the way up to AN. And from that, we're going to choose our objects in a row from the n such that after each object is drawn, basically it is returned. To the population. And it is returned to the population, this is important, before the next object is drawn. Okay, so 52 cards, you draw one, and then you put it back in the deck. And then maybe it's shuffled, and then you draw another one, and then you put it back in the deck. And you keep putting it back in the deck until you've drawn R of those objects. So n distinct objects, and we are choosing R of those objects in a row from the n, and then we return it before the next one is drawn. Okay, so basically the idea is we want to know how many total possible outcomes there are. Okay? Well, in a situation like this, sampling with replacement, it gives us an R tuple of the form, A sub I sub 1, A sub I sub 2, all the way A sub I sub R. Okay, of objects that were drawn. Okay. Where each, I sub 1, I sub 2, all the way up to I sub R has n options. right? So I1 has n objects. How many different options are there for the first object that you draw? Well, the population is n, so there are n opportunities. You put it back. You don't change the population. Second object you draw, there are also n possibilities. Okay, so basically, you know, we can use that little shortcut or theorem 1.2 or however you want to think about it, but maybe this first blank represents, you know, the first object drawn. And this blank represents the second object drawn, etc. All the way until, what's the last object drawn? Well, we're drawing R objects. So this is going to be the rth object drawn. Okay, and how many different outcomes are there for the first object drawn? Well, n. And since we're sampling with replacement, we put the object we took back into the population, which means there is also n possibilities for the second one and the third one, all the way up to the rth one. So that means that the total number of outcomes that we have is going to be n times n times n r times. Remember, the shorthand for repeated multiplication is exponents. So this is really n to the rth power. Okay. Now, let's talk about sampling without replacement. Okay, so how are we going to sample without replacement? Well, now, after an object is drawn, after it's chosen from n distinct objects, it is not replaced. Okay, so we're still going to draw our objects from this population, but the population is shrinking. So we start with a population that looks like this. We start with, you know, A1, A2, dot, 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 and maybe we'll let this be A sub k, where k is just somewhere in between 1 and n. Okay. So that means that when you're drawing your first object, n1 is equal to n. Right? There are n different outcomes from your first draw. And let's suppose that the first object that you draw is going to be the kth one. So that is no longer in your population. So that means that your new population consists of the objects A1, A2, dot, 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 maybe A sub k minus 1, A sub k plus 1. But no A sub k. Okay, so the second time that you draw, there's going to be one less than the entire population. Okay, so another way of expressing that is with the little blanks. So capital N is going to be blank, 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 all the way up until the last blank, where this still represents the first object drawn. That one's the second object drawn. That one's the third object drawn, all the way until the rth object drawn. Well, let's see what we get here. So the first object drawn, we just said n1 is equal to n. But the second object drawn is not n anymore. We've just taken one of the objects out, so you now have n minus 1 to choose from. Well, at that point, you've just drawn two objects out of your population, and if you want to draw the third one, you're going to have n minus 2 options to choose from. Okay, so this is going to go on until the rth object. And then what do you think is going to go here? Well, let's look at the pattern. So the second object that you draw is n minus 1. So this number is always 1 less than this number. This number is 1 less than this number, which means that this should be 1 less than r, which is r minus 1. Okay, so 2 and then 1, 3 and then 2, r and then r minus 1. So that means that the total number of outcomes you have is equal to n times n minus 1 times n minus 2 all the way up to n minus r minus 1, or if you distribute the negative, it's usually denoted n minus r plus 1. Okay? Because you haven't yet drawn the rth object, so you can't eliminate r of them, so you have to add one back. So that is sampling, that is sampling without replacement. And keep those in mind. So anytime you have a situation in which you're trying to find capital N and you're sampling with or without replacement, you can just use those as facts. Okay, or you can just use the blanks really quickly and just immediately get the answer. Okay, let's move on to another example. Okay, example 4. Suppose we place r distinct objects in n boxes where no box can contain more than one object. Okay, so the idea is, you have, I don't know, you can think of it like an ice cube tray if you want. And you have maybe n of these boxes, and I have r of them, and no box can contain more than one item. Okay, so maybe one item, one item, one item, one item, one item, and that's fine. So we want to know the total number of ways that that can happen. Well, first thing that I want to know is that this is impossible if r is greater than n. Why is it impossible? Well, suppose that I have even more objects. Eventually, when r is equal to n, one more object is going to put 2 of them in one of these boxes, and that just can't happen. Okay, so there's actually a rule behind that. And I just want to comment this really quickly in case this ever comes up. This is actually called the pigeonhole principle. And as dumb as it sounds, like why do we need a whole principle that says that, we can't put more than we have into boxes? Well, it's actually very useful in set theory and combinatorics, so if it ever comes up. So we have to assume that r is less than or equal to n. And we want to figure out the number of arrangements of r objects in n boxes. Okay, so let's think about that for a second. You are now doing the physical placing. You're not taking, but you're placing objects in boxes. So let's say you have a situation in which, I don't have any dots anymore. So maybe I start off like pretty blank. I'll just make this a little easier. And we want to figure out how many different ways to put objects in the first box. And when I say first box, I don't mean like this one. I just mean the first box that is going to have any of these boxes. The first time you put something into a box. And maybe this is going to be, the second box that you place an object in. and so on and so forth until this is the rth box. You can't repeat boxes, as we've said. So let's just do the math. Well, how many different boxes are there to choose from in the beginning? Well, there are n boxes to choose from, right? I can choose this one, this one, this one, this one, this one, or this one. But after I choose my first box, let's say it's this one, now I have one less to choose from because I can't double dip. So this is going to be n minus 1, which means the third box is going to be n minus 2, and so on and so forth. So we get the exact same thing as in example 3. And I want you to think about kind of the connection between that. The wording is different, right? This says how many different arrangements of R objects in n boxes. But really, if you think about it, this is no different from sampling without replacement, right? Because the layout of those n boxes, it is kind of sampling without replacement. But instead of taking stuff, you're putting stuff in a place. And when you put an object in a box, it's fixed. You can't move that anymore, and you essentially take it out of the population. And the new population is one less than the original one. Then when you place a second object, the population shrinks by one again and again. So really, it's just two sides of the same coin. Okay. Okay, now I want to do one more example. So let's get to it. Okay, so here's our final example for today. It says a subway train made of n cars is boarded by r passengers, each entering a car at random. What is the probability that each passenger ends up in a different car? Okay, so just to review, a subway is this long train that rides underground in the bigger cities, and it is, of course, made up into compartments that are called cars. And since the subway is so long, the people get on at different sections of the subway. And we want to know that if it's boarded by r passengers, where, of course, r has to be less than or equal to n for this to work, we want to know the probability that each passenger ends up in a different car. So this is not asking for a number of outcomes anymore, it's asking for a probability. So the first thing that I always like to do with probabilities is assign an event. So let event A be each passenger getting in a different car. And recall that the probability of A occurring is the number of ways A can occur divided by the total number of outcomes. What is the total number of outcomes? Well, the total number of outcomes we have r passengers, so we have r trials, so to speak. First trial, second trial, all the way up until the rth trial. And for person number 1, they have n cars to choose from, right? For the second person, they also have n cars to choose from. Because the total number of outcomes, some of those outcomes, each passenger is not going to end up in a different car. You could have outcomes where all of them end up in the same car. Okay, so this is also going to be n. And the last passenger still has their choice of any of the n cars. So the total number of possible outcomes is n to the r. Right? Well, what is the number of outcomes that produce A? Well, in order to produce A, you essentially have to kind of sample without replacement. Because as soon as a passenger boards a car, you have to remove that from the population, and then the next passenger has n-1 different cars they can choose from. Okay, so going back to this, it's a little different because now the first person has n options, the second person has n-1 options, and so on and so forth until n-r plus 1 for the rth person. So therefore, the probability, all we have to do is we just take this divided by that, and we get our answer. So in this case, we have that the probability of such a situation emerging is going to be, n of A is all these multiplied together, and capital N is all these multiplied together, which was n to the r. So our final answer is going to be that the number of outcomes was n times n minus 1 times n minus 2 times all the way until n minus r plus 1. And the total number of outcomes is just n to the r. Okay, I'm going to go ahead and stop here for this video. In the next video, we're going to talk about combinations and binomial coefficients and see how that kind of changes the game for us. See you there. Thanks so much for watching.